Two blocks are connected by a string of negligible mass that passes over a massless pulley that turns with negligible friction. The mass M2 of block 2 is greater than the mass M1 of block 1. The blocks are released from rest. So we're going to draw a free body diagram for each of the two blocks. They each have a gravitational force acting straight down. But remember, gravitational force is m times g, and these two blocks have different masses. So these two gravitational forces are not the same, so we've got to find a way to differentiate them. So I'm going to call it Fg1 for the gravitational force on block 1, and Fg2 for the gravitational force on block 2. Then they are both connected to a string on the upper part of the block. So that is tension. So we have an Ft and an Ft. And do we need to differentiate between these two tensions? And the answer to this one is that since the pulley is massless and frictionless, the tension is the same throughout a string that passes over a massless, frictionless pulley. So these two tensions are actually going to be equal to each other. And those are the only forces acting on those two masses. So in part B, derive the magnitude of the acceleration of block 2. So let's focus just on block 2, and notice that since block 2 is heavier, it's going to be accelerating in the downward direction. So I'm going to indicate that by drawing this squiggly arrow kind of separate from the free body diagram and labeling it as the acceleration. And while I'm at it, I'm going to go ahead and say that block 1 has to be moving in the upward, accelerating in the upward direction. And because the blocks are connected, they're going to have the same acceleration. It's not like one block can accelerate faster than the other block, otherwise the string would break. So, let's look at block 2. Since block 2 is accelerating, we're going to write down Newton's second law for the vertical direction, for the y direction. So, Newton, the net force in the y direction equals ma. But because this is block 2 we're looking at, we need to actually write this on the mass. So we're going to call it m2a. Now, the forces on block 2, we're going to take remember the positive forces minus the negative forces, and we always define the positive force, the positive direction, by whichever way the acceleration is pointing. So on block 2, the acceleration is in the downward direction. So this is going to be our positive force, and this is going to be our negative force. So the net force here is going to be Fg2 minus Ft. Fg2 minus Ft is equal to m2a. And we have a formula we can plug in for the gravitational force. The gravitational force is mg minus Ft equals m2a. Remember, we're still talking about block 2, so on this mass, we want to make sure that we indicate that is block 2. So the formula now is m2g minus Ft equals m2a. So notice that we want to express the answer for the acceleration in terms of m1, m2, and fundamental constants. We have an m2 in this equation, but the Ft, we don't know what that is, and we can't express the answer in terms of Ft. So the way we get Ft is we go over to the other block, the other free body diagram, and let's just go ahead and draw or set up a Newton's second law for that one. The net force in the y direction is equal to mass times acceleration, but since this is block 1, it's going to be m1a. Now for this one, we said that the block was accelerating in the upward direction, so this is now going to be our positive force, the Ft, and then this will be our negative force. So we're going to write Ft minus Fg1. Ft minus Fg1 is equal to m1a, and when we plug in the formula, Ft minus mg, or m1g, is equal to m1a. And now we have a second formula where Ft is the only unknown in this formula. So now what we can do is we can take either one of these two equations, solve it for the Ft, and plug that into the other equation. So for example, if I take this blue equation and just rearrange it to get Ft by itself, just bring the M1G over to that side, we have Ft is equal to M1A plus M1G, and then you can go and plug this Ft into this other equation. So we have M2G minus, in parentheses, all of this stuff, replacing the Ft, M1A plus M1G, close the parentheses, equals M2A. Now, this whole equation has an A in it in two separate places, right here and right here. And the A is what we're solving for, so we want to move all the terms with an A over to one side of the equation and factor it out, and that will allow us to solve for the A. So let's go ahead and distribute this minus sign into the parentheses. So we have M2G minus M1A minus M1G equals M2A. Now I'll do two steps at once. I'll bring this negative M1A over to this side of the equation and factor out the A at the same time. And I guess while I'm at it, what's left on this side of the equation, the M2G and the minus M1G, I'll go ahead and factor out the G. So that leaves me with M2 minus M1 in parentheses with the G, that's these two terms circled in green with the G factored out, is equal to, and on the other side of the equation, we have M1 plus M2 times A. That is this term brought to the other side and made positive with the A factored out, so we have M1 plus the M2 left. And now, if we just divide both sides of the equation by M1 plus M2, you'll have the expression for A. So A is equal to M2 minus M1 times G divided by M1 plus M2. Okay, part C. So each block is replaced with a block that has double the mass of the block that it replaced. Does that cause the acceleration of block 2 to increase, decrease, or remain the same? So if you look at the equation that we just derived for the acceleration of block 2, and technically also the acceleration of block 1, since they have the same acceleration, if we doubled all the masses, what would it look like? So we double the M2 at the top, the M1 at the top, the M1 at the bottom, and the M2 at the bottom. And notice that means you could factor out a 2 from the top and be left with this, and you could factor out a 2 from the bottom and be left with this. The 2's would cancel out, and you end up with the exact same expression. So that means the acceleration would remain the same. And to justify the answer, you can just show that one with the calculation with all the numbers plugged in and canceling out if you want to. And finally, for part D, does the tension in the string, does it cause the tension in the string to increase, decrease, or remain the same? Well, notice we haven't actually calculated the tension explicitly, but if you look back earlier, we actually kind of did. Because right here, when we rearrange the equation, we rearrange the equation for the tension. So if you look at this equation, we have Ft equals M1A plus M1G. So if we doubled both masses, what would happen? Well, we already know that this acceleration remains the same. We just proved that in part C. And we know that G is a constant, that remains the same. But this equation does have an M1 in it in two separate places. So doubling the masses will double each of these terms. That 2 can be factored out, but overall that still means this entire thing is doubled. So the tension will increase in part D. And you can once again justify your answer just by showing it with the equation.